Hello. I'm Wei Chen, and Penny Zheng and I are from Arm open source software automotive and industry solution team. In today's solution, we want to introduce our work of porting Zheng to Armv8-R AArch64 platform, and we will introduce current work status and expanded Zheng capability like static allocation and direct map. Armv8-R is the latest generation ARM architecture targeted at the real-time profile. It introduced virtualization at the highest security level while retaining the protected memory system architecture based on MPU. In last year, ARM announced CoreTOS-R82, which is the first ARM 64-bit CoreTOS-R process based on Armv8-R AArch64. Let's start with a quick look at some of its major features for engineers. And we have several features that allow us to design and implement high-performing processes for safety-critical environments, and includes the first one. Oh, sorry. Where's my? I'm missing one slide. So the slides is not very. It's not the same as I upload to the website. Okay. So I have to use the. The first feature is that Armv8-R doesn't support memory region overlapping. This is a new feature in Armv8-R. If you had used CoreTOS-R series process before, like CoreTOS-R5 or CoreTOS-R8, you may be very familiar with MPU memory region overlap. In these processes, one memory region can be configured in multiple MPU protections and with different attributes. Each MPU protection region has a priority. If you configure a memory region in two MPU protection regions, the higher priority region's configuration determines its memory, its attributes. And this design is flexible to use, but the software and the hardware will become more complex. In Armv8-R, the memory region overlap is not allowed. One memory region can only be configured in one MPU protection region. The MPU protection region doesn't have priority anymore now. And the hardware and the software can be simple and brings the system more deterministic. And for Armv8-R, the next new feature is that new exception models that is compatible with Armv8-A. For example, the CoreTOS-R82 exception model is compatible with Armv8-A AArch64. Zheng has already supported Armv8-A exception model, so this can be reused in our work. The third is that Armv8-A introduced a virtualization support for guest OS compared to the Armv7-R. This is a new feature because hypermode or EL2 exception level has been added to Armv8-R processors. And this makes hardware-supported virtualization become possible on CoreTOS-R series. And this feature is also the origin of our work. Okay. The last feature update is about the floating point. There's some enhancement of the floating point. Yeah. But it's Zheng hasn't involved too much about it, so we will skip it. Okay. That's for Armv8-R, but for Armv8-R AArch64, there still have some update. The first Armv8-R process is the CoreTOS-R52. It's a 32-bit CPU. And now in the Armv8-R AArch64, we added 64-bit execution capabilities and up to 48-bit physical addressing to the classic ARM real-time process architecture. Because in modern products, we are seeing designs in which larger memory addressing is becoming necessary. The memory requirements of these products come near to the 32-bit 4 GB memory addressing limit. In Armv8-R AArch64, up to 1 TB physical addressing ability will meet these requirements. And they also have some update enhancement of the floating point. And the important one is that for improved security, the Armv8-R AArch64 supports 3 exception levels for compatibility with trust zone-based systems. They are secure year 2, secure year 1, and secure year 0. The secure year 2 is the highest privilege, and the trust firmware, and they may need coexist in this exception level. This would be a new challenge for them, but is another big topic. We will not discuss it in this session, as there are optional MPU and MNU in secure year 1. So we can run virtuals or RTOS in this exception level. The secure year 0 is still running some application workloads. Yeah. And for AArch64 Armv8-R, there still has some difference from the Armv8 AArch64. The first one is that Armv8-R only supports single secure state, but Armv8-A supports secure and no secure 2 status. Current Zheng is designed for no secure year 2. On Armv8-R, Zheng will run in the secure year 2. As most system registers in the secure world have bank registers in no secure world, so switching words doesn't bring too much changes. The secondness is that in Armv8-R we don't have year 3. Now both the Q timer and hypervisor timer can be used in secure year 2. But in current work, we keep the Zheng to use the hypervisor timer, as we have done for Armv8-A. In ISA level, there has some difference. Armv8-A is still compatible with the suppose A64 instruction set, but some instructions have been modified. There are very few. They are all of them are barrier instructions. The DSB and DMB has been refined. They in their behaviors in year 1 and year 0 are relative to the VMID. And if you run barrier instruction in year 2, the scope will only affect the in year 2. And we also introduced a new instruction, various instruction DFB. Yeah. But from the time being, these changes have no effect on Zheng. Yeah. The following two differences are related with what we are working on. The Armv8-R provides a PMSA-based virtualization model. In a PMSA system, we are using virtual address to determine the access permissions and memory attributes. And this is also what Zheng is using now. But on Armv8-R, AArch64 platforms, the PMSA use physical address to determine access permission and memory attributes. This means we must decouple Zheng with VMSA. And currently, the address translation in PMSA, the address translation where flag maps the VA to PA for year 2, flag maps the IPA to PA for year 1 stage 2. This means Zheng could not map physical address to virtual address like it has done with MPU. The mapping and remapping functions could not be supported on Armv8-R AArch64 platforms. At the same time, Zheng lost the ability to translate get physical address to host physical address. What address that gives out is the target address that will be sent to bus. This will have a significant effect on the current working mode of Zheng. How to adapt to these changes is what we focus on in these slides. We are using for Armv8-R. You can obtain this simulation from Arm's website. It's a public free simulation. Armv8-R82 implements secure year 2, secure year 1, and secure year 0. It has an MPU with 32 protection regions in year 2. In year 1, users can choose to use MMU or MPU. If users select to use MPU in year 1, it also has 32 protection regions. This is our objective of view. We want to run mixed criticality workloads with hardware level isolation. We will run Zheng in Armv8-R AArch64 secure year 2 with MPU supports. Then we want to create two virtual machines. For one virtual machine, we will configure it to use MMU in year 1. And this virtual machine will run RTOS like Linux. And it's responsible for running the more complexity algorithms and higher level applications. Another virtual machine we will configure it to use MPU in year 1. This virtual machine will run RTOS like Xavier or FreeRTOS. It will run some real-time workloads like AArch64 series have been until now. And then we'll use year 2 MPU to isolate the real-time workloads and rituals. And obviously, once we replace the MMU with MPU in year 2, we will no longer have the 12-bit miss overhead, nor the MMU page table work overhead. The deterministic data access latency for the entire system will be more better. But at the same time, it's also clear that we will lose more flexibility than the MMU. But I think this is a trade-off. Yeah. About the lost flexibility, let's see kind of Zheng memory layout. This memory layout is based on MMU. The physical address space layout of Zheng image memory, RAM, and peripherals may be quite different on different platforms, but Zheng can use MMU page table to reorganize them into the same layout in the virtual address space. This flexibility is now lost with the use of MPU in year 2. Zheng should be linked to the address where it runs from in MPU system. And except Zheng itself, Zheng also provides a virtual machine memory layout template. It benefits from the MMU's stage 2 address translation. Zheng implements P2M table for each virtual machine. Depends on P2M table, Zheng can map discrete physical addresses into a linear guest physical address space. And all guests can have the same guest physical address layout, but after we change to the MPU system, there's no stage 2 address translation. When Zheng allocates memory or assign device to guest, the guest only can see the physical address of their resources. If they are non-contiguous in physical addresses, you may probably run out of the MPU protection regions. And if you allocate too many discrete chunks of memory, which and it also may exceed the max number of guest hours can tolerate. For example, Linux can support up to 128 initial memory blocks. And if we are using current Zheng memory application to allocate memories for guests, there is a probability of allocating more than 128 memory chunks. And this is not a problem in MMU system, but in MPU system, this would be a problem. And so here, let's see the challenges we will encounter in the MPU in a MPU on PMSA system. And if we want to make Zheng to work properly with MPU, first, we don't have year 2 MPU. Zheng depends on year 2 MPU to manage year 2 stage 1 access permission and attributes. And second, we don't have year 1 MPU stage 2 translation. So guest doesn't have independent guest physical address space and can only use current IPA memory layout. It also depends on year 2 MPU to isolate memory with other guests. And the third one is that Zheng year 2 stage 1 and the guest year 1 stage 2 are sharing limited year 2 MPU protection regions. The mask protection region number can be 256, but the number of a typical implementation is 32. And current Zheng and guest memory allocation will create more fragment chunks. So what can we do? Okay, I think I will give the left hand to Penny, and she will introduce our current solution. in MPU system to solve these challenges. Penny, can you?
Yeah. Please,
yeah, okay.
Next slide. Yeah.
Okay.
Hi, this is Penny. The first feature I may introduce here is static allocation of memory resource, which refers to system or subsystem for which memory areas are predefined by configuration. There exists two kinds of static allocation. One is system on static allocation and the other is subsystem aka domains on static allocation. I will briefly introduce both here. As for system on static allocation, user cases involved here may be as follows. In safety world, users prefer the whole system to behave predictably, so the then heap shall be static too. A very draft picture in the left, you could see that the blue block points to the reserved physical RAM as then heap. The other reason why we need it on MPU system is that then heap on static allocation could reduce protection region fragmentation. Please, next slide. So during implementing the MPU system on Zheng, we found out that in normal cases, besides reserved memory boot modules, such like the image code, guest kernel, or the left-free memory will go to heap allocator. So the memory layout may just look like the left pic here. Heap as tiny holes sit across all the memory, and we need to give each memory block one MPU protection region, since they have different memory attributes. See the picture here. There are 4 protection regions. Protection region 2, 4, 6, 8 are all for the heap. But in reality, the number of MPU protection region is small and limited. The way using it like this is wasted. But if we are introducing then heap on static allocation here, the MPU region layout will turn out to be the right, which the arrow points to. Previous 4 pinky scattered protection regions as heap now reduced to 1. Please next slide. Like I said before, the other kind is domain on static allocation. About domains on static allocation, the user cases involved here may as follow. In safety world, users prefer a system having a predefined non-changing behavior, so memory resource for domains shall be static. Statically partitioned embedded system with no DOM 0 shall have statically configured memory resource. And normally, guest RAM allocated through heap allocator could be composed of multiple memory blocks in size of power of 2. Those memory blocks could be scattered and a waste of MPU protection regions. Please, next slide. Here I list a simple example to show what domains on static allocation looks like in US tree. Domains on static allocation is supported through static memory nodes defined in reserved memory node, with then static memory domain compatible, which are specifying physical RAM blocks as this domain's guest RAM. See from the right picture here, two blue physical RAM blocks are reserved as guest RAM for DOM U1. Please, next slide. Another feature I may introduce here is one-one direct map. One-one direct map feature is necessary for MPU system, but still the user cases included here is not only restricted to MPU system. This feature addresses that guest physical address must be equal to physical address in stage 2 address translation. User cases where DOM U needs one-one direct map include the following scenarios. IOMMU disabled if it doesn't cover a specific device and all the guests are trusted. Thinking a mixed scenario here, where a few devices with IOMMU and a few without, then guest DMA security still could not be totally guaranteed. So users may want to disable the IOMMU to at least gain some performance improvement from IOMMU disabled. Another scenario is that IOMMU disabled as a workaround when it doesn't have enough byte ones. To be specific, in a few extreme situations, when multiple devices do DMA concurrently, this request may exceed IOMMU's transmission capacity. IOMMU disabled when it adds too much latency on DMA. For example, TLB may be missing in some IOMMU hardware, which may bring latency in DMA progress. So users may want to disable it in some real-time scenario. The last two are the major reasons why we need 1-1 direct map in the MPU system. IOMMU is not present in the system. This is exactly Cortex R82 belongs to. And the last but not the least scenario, virtualization address translation in EL2 is missing on MPU system. So GPA must be equal to PA. Next slide, please. Here I drew a picture to show you what the 1-1 direct map looks like. I list two domains to compare here. As for domain U1, it is a normal domain. 1 GB guest memory is requested in the device tree through memory property. During setup, the heap allocator will allocate physical RAM of 1 GB as its guest RAM, and this physical RAM will be mapped to the fixed guest RAM 0 base address 0x470. And as for domain U2, it is a 1-1 direct mapped domain. Direct mapped property must be added to device tree, and you could see from the picture. Now it is not mapped to the fixed guest address base address, but the same one as physical address. Next, please. Here I may share some design on the reducing protection region fragmentation. During the MPU implementation, we found out even with Zheng heap on static allocation, the MPU protection region could be in short supply, since the MPU protection region resource is very limited. In general, memory in Zheng system could be classified into 4 classes: Zheng image section, Zheng heap section, guest RAM section, boot module section. And as for Zheng image section, here we do detailed division on Zheng image based on different memory attributes. At most, it needs 5 protection regions to describe. Protection region 1 to protection region 5 in blue. The next is Zheng heap section. Zheng heap on static allocation is supported. In picture, protection region 7 and 9 are reserved as Zheng heap in right. And continuously, guest RAM section. Domain on static allocation is requested here. In picture, protection region 8 in yellow are reserved guest RAM for domain U1. Last but not the least, it is the boot module section, including guest kernel init-refs, device pass-through binary, actuator. You may say that after initialization, boot modules will be free, then memory will be going back to heap. But at least at some point during boot up, the memory layout could look like the pic drawn here. If 1 protection region for each memory block, it already costs 10, not mentioning that we only bring 1 guest here. Next slide, please. Sorry. Back to the previous slide. Yeah. And then the actual reasons behind this are that, after all, Zheng doesn't have any layout restriction for memory. Users may place boot modules anywhere, users may reserve Zheng heap memory anywhere, and users may reserve guest memory anywhere. Now, the next slide, please. So we are thinking that an ideal memory usage layout could be like this. User needs to configure 1 boot module section to limit the placement of all boot modules, like all guest kernel modules or device pass-through modules. Here, protection region 6 points to this section in the picture. User also needs to configure 1 Zheng heap section to limit the placement of Zheng heap on static allocation. Then, see picture here, reserved heap must be located in protection region 7. Also, user needs to configure 1 guest RAM section to limit the placement of domain on static allocation. All guest RAM must be placed inside protection region 8. Then it is 1 protection region for each section. Now the previous protection region 6 to protection region 10, the total 5 protection regions reduces to only 3 protection regions. And even with more guests in, only memory in boot module section and guest RAM section are used, but will not cost extra MPU protection regions for them. And also when doing context switch between Zheng and guests or 2 guests, for now only needs to disable the region as guest RAM section. MPU protection region as Zheng image and Zheng heap will stay enabled and unchanging, not like before we need to disable the whole MPU system to update. Next slide, please. Now let's do some RAM up here. Since EL2 MPU protection regions resource are very limited, and several components will share this resource, like the Zheng self-memory management, which I talked a lot in previous slides. Guest P2M MPU-based configuration and transform well for Armv8-R AArch64 are also taking up MPU protection regions. So in conclusion, the pros of restricting memory usage to fixed regions includes like reducing the protection region fragmentation, reducing the complexity of memory management, making the whole system static and forcible, and saving more MPU protection regions for guest P2M configuration, which means more discrete guest memory blocks may be tolerated. And in the future, when implementing virtual devices, it leaves us more MPU protection region to enable for such things like shared info event channel. Next slide, please. And about current status of our work on Armv8-R AArch64. Briefly speaking, Linux and Defi both could run as Zheng guest on FWPR82. And our work now completes the following changes. Modify Zheng system initialization to adapt Armv8-R AArch64. Decouple Zheng from PMSA to also support PMSA. And MPU support in Zheng memory management subsystem. And MPU-based P2M to support stage 2 address translation. Extended context switch to cover EL1 MPU related registers. Here I will show a demo on running Linux and Defi on Armv8-R FWP. Please show the demo. Could you see the? Could you listen to the audio?
Yes.
Okay. You hear no audio from the video?
Yeah, I can.
We cannot hear any audio from your video, Penny.
Oh my. Okay, let's just I will describe here. So there are 4 consoles here, and the first one in the left upper is running FWP R82 script, and now the log is for the Zheng log, and the right. And you could see from here, this is the Zheng MPU configuration for the Zheng memory. And now I am pointing to the Zheng setting up the first DOM U1. And I'm pointing to this log. This log is for the domain on static allocation, and those preserved physical rhyme are reserved for DOM U1. And now it's printing out the early print key of the DOM U2, and the DOM U2 is the Linux guest. And you could see from here, which my cursor points to, this is the AArch1 for the Zephy guest, and the Zephy guest is running, and they are running the hello world as an init process. And let's back to the AArch2, and the AArch2 is the runtime console for interacting with the Linux guest. And we are running init script as an init process. And I may speed up in this video. And finally, the Linux guest is totally on, and I can log into it. And I run a very simple ls command here, and it is working, and the whole video is finished. And for there are still several limitations here on current implementation. DOM 0 last configuration is necessary, which means no PV device support yet and only pass-through device supported. Static allocation feature and 1.1 direct map feature are also needed. The patch version 1 has already been uploaded to upstream for review. Guests can be only created by device tree XL, not ready at this time. Alternative framework has also been disabled, and all ending removing guest memory actions in runtime are not supported too. Since the number of protection region is small and limited, only support limited guest discrete memory blocks. All shared memory between Zheng and VM or 2VM is not ready, including event channel, grant table, shared info. Then also virtual device IRQ injection is not ready too. Please next slide. And it is the last slide as a to-do list. We will prepare all the changes to the upstream to the Zheng community for review, and we are going to support alternative framework in MPU system, virtual device support in MPU system, and inter-VM communication in MPU system. That's all. Thank you for listening.